Okay, let's just rip the Band-Aid off right away. We are completely obsessed with thinking AI right now.
Oh, absolutely. It's the flavor of the month.
Yeah, you literally can't scroll through your feed or open a tech newsletter without seeing someone hyperventilating about System 2 thinking.
It's everywhere.
And the narrative is so seductive, right? It's this idea that if an AI just pauses, takes a deep breath, and produces this long chain of thought before it answers, it suddenly turns into Einstein.
Right.
We see it with OpenAI's O1, we see it with DeepSeek R1. The underlying logic is just that slower is better. Showing your work is the gold standard.
Well, it appeals to our human intuition.
Yeah.
I mean, we tell school children, don't just guess, show your steps.
Yeah, partial credit.
Exactly. We inherently believe that the process of reasoning, making a mistake, catching it, backtracking, and trying again, is just superior to glancing at a problem and shouting out an answer.
Right. But here's where it gets really fun for our deep dive today. We have a new paper on the desk titled To Backtrack or Not to Backtrack.
It's a great title.
Very Shakespearean. And the researchers, a team from Harvard and the Kempter Institute, basically looked at that core assumption and said, actually, you might be wasting your time.
Which is a bit of a heresy in the current climate.
Total heresy.
They are essentially asking, when is thinking actually just expensive noise?
I love a good counter-narrative. So set the stage for us. This wasn't just a philosophical paper, right? They set up a literal cage match.
They did. They pitted two heavyweights against each other to see who could solve problems more efficiently. So in the red corner, you have the System 2 style approach. Technically, this is called sequential autoregressive search.
Which is a mouthful. Let's just call it the backtracker.
Fair enough, the backtracker.
Yeah.
This is the model that mimics human reasoning. It writes down a step, maybe realizes it made a mistake, backtracks, corrects itself, and keeps going.
It leaves a trail.
Right, it produces a trace of its thought process.
Okay. And in the blue corner?
We have parallel sampling, or the direct solution approach. This model doesn't show its work at all. It doesn't backtrack. Instead, it looks at the problem and takes a guess. But, and this is the crucial difference, it takes 50 or 100 guesses simultaneously, all in parallel.
So instead of one genius working methodically for an hour, you have a room full of interns all shouting an answer at the exact same second, and you just pick the best one.
That is a vivid way to put it, but yes. And the metric here is really critical for you to understand. They didn't just measure pure accuracy. They measured efficiency using a fixed compute budget.
Which is the great equalizer in AI right now.
Exactly. If you have, say, $10 worth of computing power, or FLOPs, how should you spend it? Should you pay for one long, thoughtful, backtracking chain of thought, or should you pay for 100 quick parallel guesses?
I think most people, myself included, would probably bet on the thoughtful genius. We really value the why and the how.
Sure we do.
But the results of this paper are messy. To test this, they used games, specifically Countdown and Sudoku.
Two very specific, deliberate choices. They represent two fundamentally different types of cognitive loads.
So for anyone who didn't grow up watching British TV, let's quickly define Countdown. It's a math game. You get a target number, say 16. Then you get a handful of smaller candidate numbers, like 96, 11, 78, 22.
Right.
And you just have to use basic addition, subtraction, multiplication, and division to hit that target.
It's arithmetic, but it's highly combinatorial. You shuffle the numbers around to find the right equation.
And then Sudoku is, well, it's the classic logic grid. You fill in the missing numbers, so every row, column, and square has digits 1 through 9.
Now, here is the actual setup. The researchers trained small language models based on the Qwen 2.5 architecture, mostly around 17 to 144 million parameters, specifically for these games.
Build from scratch.
Built from scratch. And they created two versions for each game. The backtracking model was trained on data that literally showed the struggle.
What does that mean, showed the struggle?
It saw the computer trying a path, hitting a wall, and going back. It learned the process of searching. The underlying algorithm was depth-first search.
So it literally learned how to struggle.
Correct. Now, the direct solution model was trained only on the correct answers. It never saw the mistakes. It just saw, here are the numbers, here is the solution.
So one learned how to solve, and the other just learned the final answer.
In a sense. And then they ran the test using that fixed compute budget. And this is where the System 2 narrative really takes a hit. Let's start with Countdown, the math game.
Who won?
The parallel method. The direct solution guesser.
And it wasn't even close, was it?
It was a landslide. The backtracking model showed what we call sublinear scaling.
Okay, translate that for us.
It means pouring more compute into making the chain of thought longer didn't really help it solve much more. It just hit a ceiling.
But the direct model.
Linear scaling. If you let it make 100 guesses instead of 10, it got significantly more accurate. It kept improving as you gave it more guesses.
So for Countdown, quote-unquote thinking was literally a waste of resources. You were better off just spamming guesses.
Yes.
But then they switched to Sudoku.
And the whole world flipped upside down.
Total reversal.
Complete reversal. In Sudoku, the backtracking model absolutely crushed the direct solution. The direct model, even with tons of parallel guesses, just flatlined.
It couldn't keep up.
Not at all. The model that could pause, fill in a cell, realize it broke a rule 3 steps later, and go back to fix it, that model dominated.
Okay, so this is the real meat of the deep dive today. Why? Why does thinking work for Sudoku but fail so hard for Countdown? The paper gives 3 reasons, and I want to unpack them because they really explain how these models actually work under the hood.
Let's do it.
The first reason is tree depth.
Right. This is about the shape of the problem itself. Imagine the solution path as a literal decision tree.
Okay, visualizing a tree.
In the version of Countdown they played, you only have 4 input numbers. To hit the target, you typically only need about 3 mathematical operations. The tree of possibilities is very shallow.
Because the answer is only 3 steps away.
Exactly. So setting up a massive, complex machinery to backtrack and self-correct for a problem that is only 3 steps deep
Is total overkill.
It's worse than overkill. It's administrative bloat. The overhead of managing the backtracking process is higher than the cost of just taking another random guess. But look at Sudoku.
Sudoku is definitely not 3 steps.
No, you might have 50 or 60 empty cells. Every time you fill a cell, that's a step. And crucially, that step constrains what you can do 20 steps later.
Right.
If you put a 5 in the top left corner, it might make it impossible to put a 5 in the bottom right corner 40 moves down the line.
So the tree is deep, and the branches are super tangled.
Exactly. The search tree is incredibly deep. In Sudoku, you cannot just guess the whole grid in one shot. The probability of getting 60 independent numbers right by pure luck is effectively 0.
You need that system 2 capability.
You have to have it to navigate the depth.
And the researchers actually proved this by hacking the games, didn't they? This was the part I found really clever.
Yeah, to prove it wasn't just about the type of game they modified them. They created a stacked countdown where they forced the math game to be deeper. You had to solve one problem just to get the input number for the next problem.
So they artificially made the tree deeper.
And suddenly, the backtracking model started winning. Then they did the reverse. They made easy Sudoku by pre-filling way more cells, making the tree shallower. And the direct model caught right back up.
So, lesson 1 for you listening. Backtracking is a tool for depth. If your problem is shallow, don't overthink it. Just guess.
Precisely. But the second reason for the failure in Countdown is honestly even more fascinating. And it exposes a major flaw in how we train these systems. They call it prescribed search bias.
Prescribed search bias. It sounds like the AI has been taught bad habits.
That is exactly what it is. We have to remember how they trained the backtracking model. They didn't just tell it, hey, figure this out. They fed it training data generated by a specific algorithm.
To depth-first search, DFS.
Yes. So they showed it thousands of examples of a computer program systematically checking every option, failing, and going back. And the AI learned to mimic that exact behavior.
So it didn't just learn how to solve the problem, it learned how to struggle like the algorithm.
Right. It learned to go down the exact same rabbit holes that the DFS algorithm went down.
So even if there was an obvious, faster shortcut, the AI would just ignore it because it was role-playing the struggle.
Exactly. It was pantomiming the search process it was shown in the data. Meanwhile, the direct solution model was only trained on the correct path. It never saw the rabbit holes. It never saw the failures.
Oh, wow.
So in Countdown, the direct model actually found shortcuts that were more efficient than the algorithm used to train the backtracking model.
That is wildly ironic. The model that was supposed to be thinking was actually just blindly following a script while the guesser found a smarter way.
It highlights a real danger in chain of thought data. If your training data contains inefficient reasoning, your model is going to learn to reason inefficiently.
Which leads us to the third reason, and this one is the most technical but probably the most important for the engineers listening, the verbosity trap.
Yes. This is where the physics of large language models comes back to bite us.
Because these models don't just think in the abstract, they generate text, and text costs compute.
Specifically, text costs compute quadratically.
Okay, let's pause right there. Explain quadratic scaling to me like I'm 5, or maybe like I'm a liberal arts major.
Okay, so these models are based on the transformer architecture. The core mechanism inside is called attention. The model has to pay attention to every single word it has previously generated to figure out what word to generate next.
So if I've written 10 words, the AI looks back at 10 words.
Right. But if you write 100 words, you don't just do 10 times the work. You have to look at every word against every other word. The complexity explodes.
Yeah.
You double the length of the chain of thought. The computational cost to process it roughly quadruples.
So a long, rambling chain of thought isn't just annoying to read on screen. It's exponentially more expensive for the computer to actually process.
Exactly. In Countdown, the backtracking model was spending massive amounts of its compute budget just writing out its search process. Like, I am trying 96 minus 78. Oh, that didn't work. Let me try 96 plus 8.
It was filling up its context window with junk text.
It was. And because the problem was shallow, that verbalization overhead was fatal. The direct model just output numbers. It was lean. The backtracker was totally bloated.
It was just yapping its budget away.
It really was.
Okay, so we have 3 problems here. Shallow trees don't need backtracking, training data teaches bad habits, and long chains of thought are incredibly expensive.
Right.
But the researchers didn't just point out the flaws, they actually tried to fix them. And this is where we get a glimpse of the future.
They did. First, they tackled the verbosity issue. They created a model called Think Backtrack.
Which I assume basically means think, but shut up about it.
Essentially, yeah. They trained the model to perform the reasoning step implicitly internally and only write down the actual result of that step.
It's like doing the mental math in your head and just writing the final number rather than writing out the whole long equation.
And it worked. By cutting out the yapping, as you called it, the performance on Countdown jumped right up to match the direct model.
Oh.
It proved that the logic of backtracking was actually fine. It was the text generation that was the problem.
That seems like a massive finding for efficient AI.
It is.
But the bigger fix, the one that really excited me when I read this, was when they moved beyond simple imitation entirely. They brought in the big guns, reinforcement learning,
Yeah.
specifically GRPO.
Group Relative Policy Optimization. This is the exact same technique used by the DeepSeek models everyone is talking about right now. This is where we finally move from imitation to discovery.
So instead of forcing the model to copy the training data, they just reward it for getting the right answer.
Correct. They took both models, the backtracker and the direct guesser, and applied this reinforcement learning. And the results were honestly shocking.
What happened to the backtracker?
It had a total resurrection. Remember how we said it was stuck mimicking the inefficient DFS algorithm?
Yeah, the prescribed search bias.
GRPO broke the bias entirely. The model realized, hey, I don't have to follow this script anymore. I just need to get the answer. It actually invented new search strategies that weren't even in its training data.
It improvised.
It optimized. It started searching way more efficiently than the algorithm that taught it. It stopped going down all those unnecessary rabbit holes.
It outgrew its teacher. That is wild. So RL fixes the bad habits problem.
It does. It makes the backtracking model highly adaptable and strategic. But there was a plot twist for the direct solution model.
The parallel guesser, did it get superpowered too?
Yes and no. When they applied RL to the direct model, it got incredibly good at one-shot accuracy, or pass at one. It became an absolute sniper. It could hit the target on the first try much more often.
That sounds great. What's the downside?
It lost its diversity. It became a one-trick pony. Remember, the whole strength of the direct model was that you could run it 100 times and get 100 different guesses, and one of them would likely be right.
Right.
After RL, if you ran it 100 times, it would just guess the exact same thing 100 times.
Oh, I see. It optimized so hard for the most likely answer that it completely lost the creativity needed for parallel search.
Exactly. It collapsed the distribution. So here's the big trade-off. Reinforcement learning makes backtracking models flexible and creative in their search, but it makes direct models rigid and precise.
That is such a crucial distinction. It really suggests that the future isn't just one mega model to rule them all, but knowing which type of thinking you need for a specific task.
It's the no free lunch theorem all over again.
So let's bring this back to the real world. We aren't all just sitting around playing Sudoku and Countdown. Does this apply to, say, actual science or math problems, or is this just a quirk of game theory?
The paper argues it applies very broadly. They validated these exact findings on Math 500, which is a standard benchmark for tricky math word problems, and GBQA, which is graduate-level science questions.
And what happened?
On Math 500, The pattern held perfectly. At low compute budgets, backtracking is a total waste. It just talks too much. But if you have a massive compute budget, backtracking catches up and eventually wins. But on GPQA, the science questions, backtracking won significantly, even earlier.
Why the difference with the science questions?
Think about the nature of a graduate-level science question. It's often multiple choice, but the reasoning requires connecting multiple, highly abstract concepts. You can't just guess the connection between a protein structure and a chemical reaction. You have to build that bridge step by step.
It's a deep tree.
Exactly. It has massive depth. So if you are building an AI to handle, say, customer service refunds, that's a shallow tree. Use a direct parallel model. Fast, cheap, linear scaling.
But if I'm building an AI to cure cancer or solve a new mathematical theorem,
You need backtracking.
Yeah.
You need the depth. And crucially, you need to use reinforcement learning to let it find its own way, rather than forcing it to think exactly like a human scientist would.
that's the key takeaway for me right there. We assume thinking has to look like what we do. But this research suggests that sometimes the most efficient way for an AI to solve a problem is something we might not even recognize as thinking.
Or that showing your work is sometimes just performance art that wastes literal energy.
I am definitely going to use that next time I have to write a quarterly report. Boss, the report is verbalization overhead. I have the answer right here.
Let me know how that works out for your career.
So, looking at the big picture, this paper really challenges the scale is all you need idea, or at least it refines it. It's not just about making the model bigger or forcing it to think longer. It's about matching the cognitive architecture, whether it's sequential or parallel to the actual depth of the problem.
Absolutely. It serves as a massive warning about the data we use. If we train AI to think by showing it human thinking, we are strictly limiting it to human speed and human inefficiencies.
Wow.
The RL results show that if we take the training wheels off, these models might find reasoning patterns that are completely alien to us, but far more efficient.
It's a bit humbling, isn't it? We want AI to be just like us, but maybe the best AI is nothing like us.
That's often the case with technology. I mean, submarines don't swim like fish, and airplanes don't flap their wings.
That's a great point.
What fascinates me the most is the implication for the future of prompt engineering. Right now, we spend so much time telling the model, think step by step, or explain your reasoning.
Chain of thought prompting.
Right. This paper suggests that for many tasks, that is actually terrible advice. We might see a near future where we have silent models that just output the answer, and we only call upon the verbose backtrackers for the truly gnarly deep problems.
A System 1 model for the speed and a System 2 model for the depth.
Exactly. And the real magic will be in the router, the piece of software that decides, is this a Sudoku problem or is this a countdown problem?
I love that. It's not about backtracking or not backtracking. It's about knowing when to backtrack.
Precisely.
Well, this has been a massive wake-up call for my own System 2 obsession. I'm definitely going to think twice before I ask a chatbot to show its work on a simple math problem.
You might be saving the planet some energy by doing that.
There you go. Green AI through pure laziness.
Yes, that's really one way to put it.
Yeah. Before we sign off today, I want to leave you, the listener, with a provocative thought. We've spent this whole deep dive analyzing how AI learns from its mistakes or doesn't. But think about how we learn. We always tell students that the process matters more than the answer. You know, it's about the journey, not the destination.
Right. We deeply value the struggle.
But this research shows that for the direct solution model, the one that never saw the mistakes, never saw the struggle, only saw the perfect answers, it actually found better shortcuts than the ones who struggled. Are we holding AI back by forcing it to struggle through the logic the way we do?
That is a fascinating question.
Or deeper yet, are we holding ourselves back by valorizing the struggle when sometimes we should just be focusing on the correct outcome?
That is a very dangerous question to ask an educator. But in the context of AI, I think the answer is a resounding yes. We are constantly projecting our own cognitive limitations onto machines that simply don't share them. The machine doesn't need to understand the pain of failure to find the solution.
Something to chew on while you're stuck in traffic? Or perhaps solving a Sudoku puzzle?
Just remember, if it's a hard Sudoku, feel free to backtrack.
Will do. Thanks for diving in with us today. We'll see you on the next one.
Take care.